Hello, today we will tell you a bit about the Monad project, which is our new software that we are currently developing, but we also want to start onboarding it to clients as soon as possible. So currently we are on a pilot with a few big companies, and we will just tell you about why we need Monad and what is Monad, first of all. So I'm Basaj, and with me is Dominika.
Hi.
We are both AI researchers at Synerise. And first, we will tell you actually not about what Monad is, but why Monad is important. So we will tell you about the state of the AI industry right now, and using Dominika's expertise and my expertise, we will share about the problems that we want to solve.
Exactly. So maybe let's start with the data.
Yeah. So a few background information for you is that Monad is focused on event data. We also call this behavioral data. And this is about basically events generated by users during their usage of your platform. You, meaning as a client, your platform, your shop, your e-commerce, maybe a bank account, or maybe an account at a telco.
Yeah.
So this is about the things that people do while browsing or buying your stuff.
So basically, when you can imagine that you have online shop or application or anything that the client is interacting with, they're creating all sorts of events. And let's stick to this name, I guess. So each action in the app, for example, the mobile app, create one event. So you can imagine that if you have like hundreds of thousands or even millions of clients that are browsing and doing something, you have like petabytes of data, an infinite stream of events that you need to transform somehow. And from our experience, it's pretty difficult for most of the companies, for most of the AI teams. So that's where Monad comes in.
Yeah, exactly. So you can think that the events are, for example, the click actions on the website, or a purchase action, or even a scroll action or a movement of the cursor on the website. So indeed, you can imagine that there is a lot of this data when people nowadays are really curious about their customers, and they record everything that's being done on the websites and on mobile apps. So from our experience, it is indeed the case that it reaches petabytes of data.
And to add to this, it's not only behavior in the app or on the web, but also transaction data is the event data as well. So let's imagine you're selling something. So like all the products that people were buying in the past is also event data.
Yeah, so basically the whole history of the user's actions on your website, let's say. And it's not all of the issues that we're dealing with, because next to event data, there is also a lot of attribute-like data, which describe the products that you have or the users. Obviously, it's not very intrusive, so usually we don't have things like their ID card numbers and their names, but still we have some demographic data, like where they live, where they have signed their agreement with a shop or provider, where they usually shop, for example. Are they female or male? What is their age, for example?
Yeah.
So we're dealing with customers who can have tens of millions of such records, because they're serving large country, for example, if they are a bank.
Exactly. And then from my personal experience, when I was starting my career as a data scientist, I was dealing with this kind of data. And it was really hard to change these streams of information about clients into compact form that could be put into the model. So although the AI is progressing, not a lot has changed, I guess, in this manner. So it's still very difficult for even an ambitious but medium-sized AI team to transform this data into something meaningful.
Yeah, it's a great problem. And currently we are gathering a lot of knowledge on this because we're currently conducting interviews with a lot of companies who have this problem. And from our experience and from what they're saying, we have discovered that usually the data is so large that they cannot process it, they cannot process individual events. So they must use some data simplifications. For example, they can only use data that is currently in a stream, that is like, I don't know, maybe a few minutes back in time.
Yes.
So they may have only a few of your clicks that you've ever done on the website. And they also use a lot of aggregates. So they cannot really get your whole history, but they can just compute maybe on a regular basis, but not so often, as sort of a summary representation of each user.
Yeah, and because of that, you basically lose a lot of information that could be meaningful for predicting future behavior of your client. So this is a big loss.
Yeah, this is, and obviously from our experience, it is extremely important how this aggregation is calculated. And usually what's done on the market is done in a very lossy way. So exactly like it just loses a lot of info. And the state of this is that you cannot really use your ideas and the models that are available because the data is so huge that you just cannot access the data.
Yeah, one could say that you have all this clouds and all this huge servers and a lot of infrastructure, and that is definitely true. And we're using this in Monad. But from our experience, it's very time-consuming to set up this kind of infrastructure. Data scientists are not really equipped to do it because it requires more software engineering, DevOps skills than data science or even machine learning engineering skills. So it's really difficult for them to dive deeper into distributed systems and all sorts of things. So this is one problem that we have. The second problem is that the state-of-the-art models developed by big tech companies, they're really good, but they're doing great on academic benchmarks. And then when you really need to put it into production, it turns out that they have all sorts of limitations, like performance limitations. So that was also one of the reasons why we dived into developing Monad.
Yeah, exactly. So when you hear about transformers, for example, or some large graph neural networks, you read about them in the publications, and actually you cannot really apply them to this data scale. So obviously the models themselves are just too big. They have billions of parameters, so training on petabytes of data really doesn't come easy. And what's also important, maybe we should also mention some competitors, let's say, to Monad, like other software that indeed can process quite a lot of data. Because Monad, obviously, as you probably discovered already, is a tool for processing large data, and it is a tool for behavioral modeling. So its goal is exactly to take the event data that users generate and to compute either just the representations of the user or some downstream models based on these representations, which belong to the class of so-called behavioral modeling.
Yeah, so maybe let's dive a little bit deeper into this mysterious representation. So basically, when you have all this transaction and all these events of the user, you can imagine this. You can imagine this as a graph. So basically, I'm a person who bought thing A, B, and C, and we're creating a graph out of my purchases. And then this is kind of mysterious way, in a sense that this is the heart of the algorithm, but for the sake of this argument, we're taking all these transactions into one long vector of numbers. And this is our compact representation of what you bought in the past. So if you're sitting in front of your computer and you're seeing all these sorts of data and you're thinking, I really would like to leverage this information, but it's hard to combine everything and there's no other way to actually do it, then I think Monad might be the answer for you.
Yeah, exactly. So many people actually, many customers that we have, they say that we don't have a graph in our data, we just have some events. And it comes as a surprise that indeed there is, the data has a graphical nature, nature. And the algorithms that are used to process this kind of data are the large graph neural models, could be also transformers, as we already said. And that's the problem, that the data, the number of nodes, we can have 30 million of users, for example, or 50,000 products. And they just interact with each other all the time.
So what would be the node here for Monad in the case of a transaction? Let's maybe explain it in this example.
For Monad, usually the node is a product. So we can imagine our whole product store, and each node is a product. And whenever the products are bought together during a single session, for example, user session, they are linked by edges.
Okay, so if I buy milk and banana, it's linked together. But if I buy milk and beer, it's also linked together. But if I don't, there is no link connection. There's no connection for my purchase. That's why we could easily find products bought together.
Yeah, because we assume that if people buy some products together, it means that there is a certain sort of people that fancies these exact products. So that's why the products could be similar under some formulation of similarity. If you have more than just two products and you bought them sequentially in your shopping cart, you add, for example, 3 products, it creates an edge where you have product number 1, product number 2, product number 3, they are connected by an edge.
From our experience, of course, there are some outliers, like people buying not usual things together. But because we're working on big data and on a lot of clients, then these outliers kind of are kind of ruled out in a sense. Yeah.
Although you can obviously detect them if you can compute the general tendency. You can obviously then say that, well, this example follows the tendency that we know. However, this client is opposite, for example, to our tendency somehow. So we say that they are an anomaly.
Exactly.
This is also very important and useful for companies that work with event data. So this is what Monad does, and this is what is currently problematic for large state-of-the-art models that are described in literature. And also this is hard for the companies that currently operate in this market, because we classify Monad as a sort of AutoML tool, and there is kind of the whole bunch of AutoML tools right now on the market. For example, you might have heard about Data Robot or Google Vertex, for example, for a lot more advanced users, so to say. So maybe let's talk about the unique functions of Monad, because you already know that it does something which other models also handle. However, let's talk about the things that make Monad different.
Okay, just before we start, I wanted to circle back to this AutoML. We call it AutoML, but fear not, data scientists. It's not like anyone can do it, because it's mostly designed for data scientists to make their work easier and not to replace them. So we do create representations of user in a fast manner that you can experiment like faster on these representations, but the model is left like you can do the models with these representations. Of course, we do provide some example models, so even if you want to be even faster, you can use them, but basically your expertise is still needed.
Yeah, totally.
Or can be needed.
Yeah. Obviously, there is a lot of difference between various AutoML tools regarding the expertise that is needed. And there are things like Data Robot, where it's designed for business people, basically, where they can just plug in the data, it just happens in a black box and they get some results, right? And there are things like Vertex, where you are expected to understand what you're doing, and you can select the algorithms and the methods that will be used to process the data. So Monad is on the spectrum, is located more, I assume, a lot more in the direction of the more complex AutoMLs, so the ones that indeed need data scientists.
Okay, yeah. So we start with, like, what's the first phase of Monad, so people can imagine what's going on. So we have this big database and we need to create these representations, and we tend to call it the fit phase. So we're fitting the data, right?
Yeah. So the first phase is all about understanding the data. Because, you know, it's I think it's assumed to take up to 80% of data scientists' time just to handle the data, do some pre-processing, do some feature transformations, maybe filter the data if there is something wrong going on, like there is some errors and not a number values and so on that we all know and like.
Yeah, and with a lot of data, you need to work with some. You need to have a lot of memory in your RAM, or you need to work with Spark, and it's still kind of a bottleneck.
It's bad, yeah. So it's both time-consuming and resource-consuming, right? This whole phase of data understanding and transformation. So the goal is to transform the data into a form that is understood by the algorithm that we want to use. So basically some numeric form. And we actually created a list of steps that's required for that, and it has a number of points, and a great majority is about just data transformations, and model training is just at the very, very bottom, and it's the cherry on top, let's say. It's the stage where the data scientist is finally happy. And and this is the stage where we have done the heavy lifting, so to say. So usually it's thought about that the training is hard, but in reality it's the data processing, because there is also a saying, garbage in, garbage out.
Yeah, definitely.
So you cannot train a model when you have not done this data processing stage correctly.
Yeah, so we have this database with data like in a database. So there are tables and columns. So we can apply fitting to each and every column in our database. And we created an automatic inference, in a sense that the monad in the fit phase, it sees the data that is in the column and it automatically decides whether to apply a transformation for decimal numbers. So if you have some kind of price or quantity, you can apply this kind of transformation to this column. If you have text, we can also transform it. And then if you have a lot of categories in a column, like I think at this point over 200, but if you have over 200 categories in a column, but it can configure it, it can be adjusted, then we apply this graph kind of thinking that we described earlier. So for each and every column, we create these representations, and it's stored in a very, very compact way on your disk, in a compact way, because it's not like we don't do what is usually done in companies, and we learned that by talking to data scientists, that they usually store huge embeddings. It takes a lot of place. It's really hard to manipulate them, but we just stored like definitions of transformations, and then when you're in the training phase, we use these definitions to change the data on the fly.
Yeah. So we do not need the place to store the full embeddings for your 30 million users, let's say, or your 50,000 products and many other entities that you might have in your data. But we just store some very small feature generators, let's say, which allow the transformation.
Yeah, and what is also exciting is that the fit phase takes really not a lot of time. It can be done even in an hour. I think our biggest, the longest it took for us, and we're still in improvement mode, was 3 hours for a year of transactions for one of the huge grocery chains. So, you know, when you're training these transformers or all sorts of big deep learning models, it can take even up to days.
Yeah,
and if you make a mistake, you need to start again and again. So it's time consuming and also resource consuming, because buying GPUs in the cloud is also not really cheap.
Especially when you're experimenting.
Exactly.
And you need to create not one model, but a few dozen models, for example, until you're satisfied, because you don't know what's going to work. Because you're doing it the first time, for example, and you have like 5 data scientists in your team.
Yeah,
which is usually the case.
And the first time I used Monad, it was really out of the box for me. It took, I think, 2 hours. And the first model I trained even without thinking too much. It was of very high performance.
Yeah.
So
I remember that you were very surprised.
Yeah, I was really
That,
surprised.
well, is this it? Like,
I thought I did something wrong, but on the contrary. So yeah, so this fit phase is really fast, and it's kind of automatic, but of course you can adjust it to your special use cases, because we allow the user to define what needs to be changed in the data. Okay, so after the data is fit, these transformations, the definition of these transformations is
Maybe
stored.
I just say one more thing on the fit phase and, before we delve further. So why actually can we get such speed, right? So what's the secret? So the secret is that we use our proprietary algorithms that are, by the way, also open source, but so we can use an experiment on your own. And these algorithms are Cliora for graph embedding. And Cliora was battle tested with a lot of models, like huge GNNs in many competitions. And it turned out that it's actually better, it's a lot simpler, and it's better in terms of performance than many huge models that are considered state-of-the-art today. The difference in speed is such that I think in KDD Cup last year, the inference stage, so the stage after training when you are predicting, took like 7 or 9 hours for the DeepMind team, who used a huge GNN, and using our stuff, it took 7 minutes.
Oh, wow.
Yeah, so it's an enormous difference, and they have four GPUs like we had. We had one.
Yeah. So.
And it can also train on CPU,
so
you don't need you don't actually need a GPU to train Cliora. Yeah. So that's why we're so fast, and also we're using MD. And this is another algorithm that goes after Cliora, and its purpose is to create a sort of
meta embedding.
Yeah, it's a compressed and transformed embedding, and the transformations allows it to be easily aggregatable. So when you must aggregate, right? When you have event data, you need to create a profile of myself, for example, and with all the stuff that I bought at a certain store. So we need to simply connect all the events that happened that I generated to myself.
Yes.
So we need to somehow just take all of the embeddings, let's say, and just make a whole meta embedding out of them. And this is what MD does in a way that allows for retaining the important stuff.
Yeah,
that was in
so
there.
if you have data, transaction event data stored in rows, you kind of need one row per client. So MD allows to, like, as you said, compress all this information from all the rows into one row.
One row, yeah. Yeah. So let's go to the transformation stage.
Yeah.
Or
So
the downstream model stage. Maybe.
Yeah. So once we have this this aggregate version, so this meta embedding from all the modalities, and by modality we mean information about user, information about her purchases, information about her behavior in the application, on the web page, anything you can think of. Once we have this meta embedding, we can start training. So the models that we already have implemented are recommendations, propensity models. So we're calculating the probability of one of the products being bought. Also, we're developing customer lifetime values. So we're predicting the value of the future purchases, and also we're predicting churn. So how probable it is that your client will churn. And I think it's super important here to say that we're not only like training these models, but we're also comparing them with baselines. And by baselines we mean not so easy, but fairly easy rules that you could do on your own without the model, because there's no need to use model if the model is on par with the rules that you could adjust to your clients. And all these models, like, they're better than baselines. So basically it means that we do find some kind of connections between data that points us in a direction that this particular client will, for example, churn. And to be precise here, maybe I'll just give an example. So when we were predicting churn for one of our clients with Monad, we converted with a baseline that was just checking whether the client was active in the last couple of days. And it turned out that the model is much better than just saying churn, no churn, based or her activity.
Yeah, and the models are also better than the models that we did ourselves. So before we produced Monad, we needed to make these models for our clients. We needed to make them ourselves. Like, we needed to manually conduct the future engineering, the data cleaning, and so on and so forth, and manually train the model. And we've also compared Monad to our models that we created ourselves, and it was better.
Yeah, and actually, this is something that we did not really stress here, that with Monad you don't have to, I mean, business knowledge is super important in creation of the model, but it can be still applicable in Monad, but you don't have to figure out all these features that you need to do. You just have even sometimes thousands of features that you put in the model, and the model decides for itself which features are important. So it's really a great use of your time that it's done in one click.
Indeed, that is what we couldn't do before, because no one can do it. When you have, for example, 5 tables, each table has dozens of columns.
Exactly.
And you need to produce a feature out of every column and think about how to transform it, how to clean it, how to do all the things that need doing. It's impossible to produce this kind of a large feature embedding. So if you're a data scientist and you know the scales of the features that you're dealing with, for example, Monad can produce feature vectors that have 30,000 numbers. So it's a really big feature vector. And you may think about whether this feature vector indeed contains all that is needed and not a lot of data that could be actually removed, right? Because we look at the tables, we see that some column doesn't make sense for a problem, we just discard it, we don't use it. And what happens when Monad doesn't know it and it takes this column, it produces features out of it. So actually we found that the later stage of Monad, where we're training some very simple feed-forward neural networks that can be actually sparse because MD representations are sparse. So there are a lot of zeros in these vectors. Then this kind of neural network is very, it tolerates the features that aren't really contributing. So they don't break the model.
Yeah, exactly. Yeah, they don't break the model. So there's only upsides to using this. There's no really a downside.
Yeah.
And besides, if you really know that you don't want to use one of the columns because of something, you can just explicitly just discard it, explicitly say it. So the way we want users to interact with Monad is by the YAML files. So anything you need to tell Monad to do can be defined in these YAML files.
Yeah, there is a lot of options to configure. So if you do want to configure something, you have a lot of things to configure. However, if you do not want to touch this, there is also a lot of mechanisms to say that indeed we are using the optimal iteration number. Indeed, we are using the correct columns, let's say, not the columns that contain a lot of noise and a lot of rubbish. So that's the secret of Monad. It also has a lot of connectors to various data sources like Snowflake, like ClickHouse, like regular files, like CSV or Parquet files. And it works in a very efficient distributed manner. So it not only has fast algorithms inside, but it also can scale to a lot of workers or nodes in a cluster.
And it's developed in Python, so it's user-friendly in this sense.
Yeah.
Okay, so maybe to sum up, the core functions of Monad is automatic scaling, as you said, on infrastructure, so distributed computations. Thanks to this, Monad is really fast. We're using all the data, so all columns and all rows. We do have automatic feature generation that speeds up the whole process of modeling and experimentation. So imagine you have a 2-week sprint and you need to produce some results to say whether you should. No chance, but with Monad there is a chance. So so it speeds the whole process. And what's also important, there is no need to stall or full embeddings. So,
it's space efficient.
It's space efficient, exactly.
Yeah. So maybe to just sum up, we also talk a bit about the competitors. Competitors, because they're not really competitors that do the same thing as Monad does. But let's talk about why we should choose Monad over DataRobot or over our legacy pipeline in Spark, or instead of, for example, the Amazon SageMaker. Yeah. So, for example, about DataRobot. DataRobot is really simple, simple to use stuff that is designed for business people, which is fine. However, it has a lot of limitations on the number of, I think it's just on the data size that it can process.
Okay.
So it doesn't really help you much if you have big data, because it's just for business people to run a quick experiment. Things like SageMaker or Google Vertex, they do have a lot of graph embedding methods. So you can have the huge attention-based graph neural network, for example. You can train it. However, you cannot really then do real-time predictions on it, because with Monad you can, using the speed that we talked about, we can achieve real-time prediction when we've already trained the model. So what happens in these large AutoMLs is that you cannot really take out your whole history to make inference on that.
Yes.
You have like two streams. You have the things that are currently ongoing and events that are being generated by me, for example. But I also have a lot of history in your database, right? So you want to join the few things and make inference based on that. So if you want to make real-time predictions with SageMaker, for example, you just need to send data to SageMaker. But you don't know how to get this data from out of your petabyte-sized database.
Yeah.
There is also a lot of other issues that actually I think we should cover more in a later episode or an article. So we'll work on making these differences clear.
And it still needs a lot of DevOps work.
Yeah.
So Monad is really easy to use by data scientists who are tech savvy, but with setting up this pipeline in SageMaker or Spark, you need like a dedicated team, basically.
Yes. And about the Spark and the things that are open source and free, well, in my experience, it's usually that there is a very old version of Spark somewhere on your company system, and you cannot really do much about it because right now it could be a bit better, but but it's hard to update this stuff because
learning
really
Spark is like
legacy.
Another history. I mean, you have to learn Spark. It's based on Python, it can be based on Spartan, but the whole idea and the whole philosophy of Spark is pretty complex. And here we're just using pure Python, so it's really easy.
Yeah. So with Spark, you just have to learn it. It's difficult. You have to do all the
deal with out-of-memory problems.
Yeah, you have to just write all this distributed code yourself. And usually you're dealing with kind of legacy pipelines when you join some company, like a bank or other financial institution or a telecom.
Okay, so I guess that's it. Thanks, Basia, for diving deeper with me into Monad, and we'll cover more functionalities in next episodes.
Yeah, thank you, Dominika, for our chat. We should be doing more of this soon. So thank you for your attention and see you later.
Yeah, and in case you have any questions, you can reach out to us.
Of course.